Alright guys, hello and welcome to the second or third lecture of Texas Financial Derivatives learning modules. This one, first off, to introduce myself, my name is Matt. I'm a senior applied mathematics major, and I'm very much interested in actuarial science and probability, interest theory, market evaluation, you name it, I'm all about it. But today we are going to be talking about probability. We're going to give a quick introduction, show you all some of the laws and theorems associated with it, and that way you'll have a good grasp on what probability means and how to compute it. So to begin with this lecture, we first need to say, what is probability? And I think I can best put it as probability is the world of mathematics associated with quantifying the likelihood of some event occurring out there in the world. Probability is used in gambling, game theory, company evaluation, but primarily probability is going to be associated with decision making and how we can best make decisions about the real world and things associated with it. And so it sounds pretty important. It sounds very useful as well. So you might be asking, how do we compute it? How do we compute the probability of some event out there in the world occurring? And so I'm going to go ahead and write that down and give you all a way that we mathematicians compute probability. It's a very standard, easy formula to think about and compute. So I'm going to write that down. So if you have some event we have, let's call it E. Say let's call E a certain event. And the probability notated by a P in parentheses with the event E, probability that event occurs is simply equal to the number of occurrences of E divided by the size of our total sample space. And when I mean a sample space, I mean if you have some sample space, we'll denote it by this symbol omega, and it'll be a collection of observations. We'll call it one, 2, all the way to observation N. And this can be anything. This can be the number of people in a crowd. This can be the number of balls in a bag, which we will use as an example in a little bit. It can be anything you want, but what's the main importance, or it can be number of books on a shelf, or anything. But what the main importance of this is that you have a sample space. You have a list of observations that you can see, or you can put into a list. And if you want to know the probability that some event, let's say it's the amount of romance books you have or crime books you have out of your entire book set, the probability that you randomly reach in there and pull out a crime book is going to be the number of crime books you have divided by the total number of books you have. That makes sense, right? All right, so let's use an example to show this. So if I have, let's say my sample space is of red and blue balls. So this time I'll call it S. And let's say I have red, blue, and blue. So I have a bag in front of me. It's a bag. It's all jumbled up. I can't see inside it. And I reach my hand down in and I try to grab some kind of ball. I don't know what I'm going to grab, but I know there are red and blue balls in there. What's the probability I reach in there and grab a red ball? Well, let's use our formula. Let's call event A, pick a red ball, the probability that A occurs is simply equal to the number of occurrences of our event, so the number of occurrences of red. 1, 2, 3. You can count them with me. That's 3 divided by the size of my sample space. Here you can see I have 1, 2, 3, 4, 5. So it's 3/5 or 60%. That's pretty easy enough, right? What about the number of blue balls in there? Well, let there be an event B where it's the number of blue balls. Probability B occurs is the number of blue balls in there. 2, you can count on it, see right there. That'll be 2, again divided by the size of our total sample space. So 5, or 40%. So if I reach into a bag and I randomly grab something, probability I'm going to get a red is a lot more likely the probability I'm going to get a blue. And that might be important if it's a game you have in front of you. If you're trying to win something and they say if you pull a red ball, then I'll give you $5, but if you pull a blue ball, you give me $5. Well, based on your odds, it's in your best interest to play the game because you have a much better chance of winning of pulling a red ball than they would of the blue ball. So now that we've talked about a sample space and what in our observations in it, and what's the probability we get some observation, I think it's important to give you all a little law of math. It's a very simple one, but it's very important when it comes to probability. It's called the law of total probability. What the law of total probability says is that the individual probabilities of all the possible events that you can have occur in your sample space must add to 1, or 100%. And this makes sense. If we have a sample space and we have a number of events that we can possibly pull from it, being red balls, blue balls, green balls, you name it, the total probability that we pick any of these individual events, if we add them all up, it must add to 100%. And so in a mathematical sense, if you label your event E sub I, where E sub 1, E sub 2, and E sub 3, they're all just individual events. Whether that be red ball, blue ball, whatever, they must add to 1. And mathematically, this is written as the summation, which is what this symbol means right here, from I equal 1 to n of probability E sub I has to equal 1, where I goes from 1 to 2 all the way to n, and n is your total number of events there. And we can see that right here, okay? We know we only have red and blue balls here. If we sum them all up, what's 60% plus 40%? 100%. Like I just said, all your events must sum to 1. If your events don't sum to 1, either you did your math wrong or you're missing out on another thing. You know, there may be a green ball. There may be a single green ball in there that we don't know about. And so this is what the law of total probability states. And so now that I've shown y'all that with the red and blue balls, I want to show y'all another mathematical formula. It's not necessarily a law, but it is very important, and it is the union of probability formula. And so I'm going to go ahead and erase some of this here, actually. So what this says is, and when I mean union, I mean the coming together of both events. When there's a union of people, it means coming together. We're unifying. That's where that word comes from. This says if you have two events, let's call them A and B. The probability of A or B occurring, and this right here means or, is equal to the probability of A plus the probability of B minus the probability of A and B occurring. This symbol means and. Now I just want you to take a look at that for a second. The probability A or B occurs is equal to the probability of A plus the probability of B minus the probability of A and B occurring. Now I'm going to show you an example of why this makes sense once I get rid of this. So let's say we have a sample space. And it is the numbers 0 through 9. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's call event A. Let's call event A numbers 0 through 5. And event B numbers, let's do 4 through 9. Now, let's use this formula that I have up here and see what actually, let's do 4 through 8. And then and then we can call a separate event. Let's call a separate event C, being the number 9. So let's say you have a bag and you can't see inside it, and on these little sticky notes or folded cards are written numbers on it. And if you pull the right number, or you pull a certain number in a range, then you win the game. Well, let's say we want to pull a 0 through a 5. What's the probability we pull a 0 through a 5? Well, using our earlier definition, it's the number of occurrences of our event divided by our total sample space. So that says the probability of A is equal to the number of occurrences of this 0 through 5. That's 0, 1, 2, 3, 4, 5. So there's 5 occurrences divided by our total sample space. And our total sample space, you can see that it's 10. So that is 5/10 or 1/2. Probability B occurs is the numbers 4 through 8. Well, we have 4, 5, 6, 7, 8. So that is also going to be 1, 2, 3, 4, 5. 5 occurrences divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the probability that C occurs is going to be 1, because there's 1, 9, divided by our total amount. Now, actually, let's do this here. Let's say if you pull a 0 through an 8, you win the game. So we want to figure out what's the probability we pull anything between these two, like either 0 through 5, 4 through 8, because that would be in the same range. So the probability that, using our formula, probability A or B occurs is equal to the probability of A, 5/10, plus probability of B, 5/10, minus the probability of A and B. What is the probability of A and B occurring at the same time? What this means is, what is their intersection? What lies within that? What lies within the middle of them? Well, you see, this one is 0 through 5. This one is 4 through 8. And so the probability you are within A and B would be if you pull a 4 or 5. If you pull a 4, that's with event A and with event B. You pull a 5, that's with event A and with event B. So that's 2 occurrences. So minus 2 divided by 10. This gives us 5 plus 5 is 10. 5 plus 5 is 10 minus 2 is 8. So that's 8 out of 10. So, yeah. 0 through 5, 4 through 8, and then 9, yeah. 0, 1, 2, 3. Oh, my bad. This should have been a 6. So yeah, that was my bad on the math. So 6 plus 5 is 11. 11 minus 2 is 9. So it's 9 tenths. That's 90%. The other 10% comes from event C. And the reason we have it set up like this is because suppose you have the probability of A. That is everything from here that we add. Then we have the probability of B. That is everything from here to here. You can see that we have overlapped this part twice, times 2. We have gone over it with here, and then we went over it with here. If we simply added these two together, we would have a higher probability than is reality. This is why we have to subtract the probability of A and B, because that is pretty much saying, well, let's get rid of this part. And then connect them. Now it is just one single flowing line, and this is how we get the probability of A and B, the entirety of it. Now, I hope this helps y'all understand unionization and the intersection, the or and the and associated probability. And so I'm going to erase some of this, and then we're going to move on. I'm gonna leave this formula up here because it's gonna be useful. So now that we've talked about what probability is, what does it mean by the probability of an event occurring? That is the number of occurrences divided by our total number of observations, our total sample space size. And we've talked about unionization and intersection of two events occurring. Now it might be important to ask, well, let's say we have two events. Does the probability of one event occurring affect the probability of another event occurring simultaneously? And this is focused on, this is a topic we call independence and dependence in probability. So I'm gonna go ahead and write what I mean by independence. So, two events are independent from one another if the probability of one occurring if the probability of A and B occurring is simply equal to the probability of A times the probability of B. Write this part down because it's going to be very useful in the following example that we're about to do. This says if the probability A and B both occur at the same time is simply the probability of A times the probability of B. And this will make much more sense when we talk about our next theorem, Bayes' theorem. Actually, let me go ahead and show that well. What Bayes' theorem says, Bayes was an amazing mathematician. He did so many things, but his main focus was conditionality. If the condition that one thing occurs affecting another thing. So I'm going to write down Bayes' theorem. Bayes' theorem says the probability of A given B has occurred is equal to the probability of A and B divided by the probability of B. And you can look at this formula, but I think it's better to put it into words. if you know some event B has already happened, then what's the probability A happens at the same time? So let me do a Venn diagram. Let's say we have two events. Here's event B, or here's event A, and here's event B. Before I put any numbers up there, if you know B has occurred, you know you're in this section, and you want to figure out the probability A has occurred, you need to figure out this little part. Think of B occurring as being your new sample space, your new omega, your new set of observations. You can forget about everything else. You're now in this new world. This, from our earlier formula, becomes your total number of observations. Now, your total number of occurrences of the event A is simply the number of occurrences of event A within B. Does that make sense? So, I'm going to put some numbers up here. I have them right here, so I'm going to go ahead and look. So, let's say that probably one second. Let's say the probability A occurs is going to be 0.4. The probability B that occurs is going to be 0.5. And the probability neither of them occur, A not occurring nor B occurring, is equal to 0.1. So let's go ahead and put what we can on the Venn diagram. This is A, this is B. The space where neither of them happen is going to be out here. And that's going to be 0.1 out there. You can see already that all of our events add to 1. 0.4 plus 0.5 is 0.9, plus 0.1 is 1. So a probability of 1 or 100% is how you can think about this. Let's first ask ourselves, are these events independent of one another? Well, let's use our formula. Let's see what it says. And let's use this up here to make sure. What we're mainly wanting to figure out is what is probability A and B. So the probability of A and B, if we rearrange this, I'll go ahead and fill this in. The probability A or B occurs if this or this, so everything but this 0.1. Well, it's going to be 1 minus the 0.1, so 0.9. What's the probability of A? That's 0.4. What's the probability of B occurring? Minus the probability of A and B occurring. Here, hold on one second. I think my math is set up a little wrong for this. Well, the A or B occurs is that, so it's going to be 0.4 plus 0.5. Here, let's change one thing. Let me give y'all the probability of A and B. So here, that can stay the same, but let's say the probability A and B is going to be 0.2. Well, that's going to be this part right here. Are these events independent? Well, for them to be independent, probably A and B equals 0.2 must equal probability of A times the probability of B. Well, let's see if it does. The probability of A times the probability of B is going to be 0.4 times 0.5. 40% of 0.5 is 0.2. So yes, these events are in fact independent because these two match. However, let's use Bayes' theorem because I think it'll help understand it a lot better. And I'm gonna erase this to do so. And let's see if this marker works. The probability of A given B has occurred is equal to probability A and B divided by the probability of B. And I'll go ahead and let me fill in the rest of this here. We know this is 0.4, so this leftover part must be 0.2. We know this is 0.5, so this leftover part must be 0.3. And you can see 0.1 plus 0.2 is 0.3 plus 0.1 plus 0.2 is 0.3 plus 0.3, 0.3, 0.2, 0.5, 0.2. So this is actually be 0.3. That makes much more sense. Yeah. Okay, good. Now the probability A and B occurs, we've just said, is 0.2. Divided by the probability of B occurring. The probability that B occurs is 0.5. What is 0.2 divided by 0.5? Well, that's simply 2/5. 2/5 is 40%, which is equal to the probability of A. Let's write this out. Probability A given B occurs is simply equal to the probability of A. So yes, independent. Happy face. Remember what I said earlier, two events are independent from one another. If the probability of one occurring does not affect the probability of the other occurring. B has occurred. The probability of B occurring does not affect the probability of A occurring by itself. This is what we mean by independence, and it's very important. And intuitively it makes sense. So this is all I had for today. I'm thinking this run about like 20 minutes or so by now, but this is a quick introduction to probability. We talked about what probability is. It's the area of mathematics that deals with quantifying the likelihood of an event occurring. We talked about how to compute the probability of events. We talked about the law of total probability, which states the sum of individual probabilities in your sample space must sum to 1 or 100%. We talked about the union of probability, which deals with the reason we subtract that other and intersection part is because we don't want it to overlap twice. And then we talked about independence and Bayes' theorem. This is going to become important later on when we try to figure out whether the stock price is going to move up or down and whether this is beneficial for us. So I thank y'all, and I hope y'all learned something, and please subscribe to the Instagram. It is at texas.fd, and please like, subscribe, and comment. You know, it always helps. Myself and one of the other educators, Austin, in this club, will be sure to get some more one-on-one help with y'all if y'all have any questions. So thank you.